How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at 6.3 stuff, line spectra, and the Bohr model. All right, so starting with number 10, it says, which of the following transitions of an electron in the Bohr model of a hydrogen atom will give off a photon with the highest energy? So if we're talking about highest energy and it's being given off, we're trying to go from high to low, and it's going to be the biggest drop if we want the highest energy. So which one's going to give us the biggest drop? Well, let's see. A, 2 to 6, that's not a drop at all. 6 to 2, well, that's a change in 4. 6 to 4, well, that's a change in 2. 4 to 6, going up, it's not dropping. And 1 to 4, again, going up, not dropping. So biggest change in energy is going to be B. So that would give us the photon with the highest energy. 11. Which of the following transitions of an electron in the Bohr model of a hydrogen atom will absorb the least amount of energy? So we're talking about absorbing. So we're going from low to high, because if an electron goes from low to high, you have to add energy to it. It needs to be absorbed. So low to high and least amount. So we're talking about the least jump. Well, that's again, take a look. 1 to 6, well, that's a plus 5. 6 to 2, that's a drop. 6 to 4 is also a drop, so it can't be B or C. 4 to 6 is a plus 2, and a 1 to 4 is a plus 3. So we're talking about the one with the least is going to be choice D from 4 to 6. All right, 12. How much energy in joules is required for the electronic transition in the Bohr model of the hydrogen atom between the second energy level and the third energy level? Well, the way that happens is we're going to have to take a look at a couple of equations. We got 1 over the wavelength has to equal this Rydberg constant times 1 over the final energy level squared minus 1 over the initial energy level squared. And then we're going to have to take a look at another equation, which is this, energy equals hc on lambda, because that's what we're going to need, right? Because, hey, we aren't given the lambda. We're trying to get energy, but I know I can rearrange this equation to give me energy. So let me rearrange this equation to get lambda by itself, and I'm going to get lambda equals hc on energy. So now I can plug these two equations in together to give me a new one. Let me substitute lambda in for that. So I get 1 over hc on energy is going to equal that RH times 1 over n squared minus 1 over n squared. And I'm cheating, all right? I know that's final and that's initial, but I'm going to stop writing that because I'm lazy. So now if I rearrange this part right here, what I'm going to get is really energy over Planck's constant times the speed of light equals the rest of that stuff. Now if I'm trying to get energy by itself, why don't I get rid of the Planck's constant and speed of light? So I times each side by hc. So I'm really going to get Rydberg's constant, RH, times Planck's constant times the speed of light times that 1 over n squared minus 1 over n squared. And then boom, that's my equation in terms of energy. So now I can plug it all in and get my energy in joules. So energy is going to equal that Rydberg constant, which is 1.097 times 10 to the 7 per meter. So that's meters to the negative 1 times h, which is going to be that 6.626 times 10 to the negative 34 joules times second times the speed of light, which is 3.0 times 10 to the 8th meters per second, times by, in parentheses, well, we're going from second energy to the third. So it's going to be 1 over 2 squared minus 1 over 3 squared. Now, which one do I put? Do I put 2 first or do I put 3 first? It doesn't really matter. All that's going to happen is it's going to change the sign. So I know if I'm going from the second energy level to the third, I know that I'm absorbing energy because I got to go up. So don't even worry about which one. Just use your brain at the end, go back and think, hey, did energy get absorbed or released? And that'll tell you how the energy changed. So now I plug a chug and I get an answer of, I wrote it down somewhere, 3.03 times 10 to the minus 19 joules. All right, because let's see, meters per meter and meter cancel out, per second and second cancel out, and I'm left with just joules. These energy levels have no units, so that's what I get as my final answer right now. 13. How much energy in joules is associated with an electronic transition in a Bohr hydrogen atom from N1 to N3? So again, going from 1 to 3, I know I'm absorbing energy, and I'm going to go back and use that equation that I figured out previously. E is going to equal that Rydberg's constant times H times C times 1 over N squared minus 1 over N squared. So now I'm just going to plug and chug. I got that 1.097 times 10 to the 7 per meter times by H, which is at 6.626 times 10 to the negative 34 joules second times 3.0 times 10 to the positive 8 meters per second, and then times by the transition going from 1 to 3. So it's going to be, 1 over 3 squared minus 1 over 1 squared, which is just 1, right? So now I just pick up my handy dandy calculator and I beep bop boop it until I get the answer of 1.94 times 10 to minus 18 joules. Because if you take a look, all right, per meter times meter over there, second times by per second, cancel out, we're left with just joules, right? That's our unit. Bada bing, bada boom. 14. What frequency of electromagnetic radiation is associated with the energy required to move an electron from the second to the fourth energy level in a Bohr hydrogen atom? All right, we're going to need a different equation. So I know that I'm going to start with this equation. 1 over lambda equals that Rydberg's constant times by 1 over n squared minus 1 over n squared. All right, but they don't want wavelength, they want frequency. So hopefully I know another equation that has wavelength and frequency together. And I do. It's C equals the wavelength times the frequency. So if I'm trying to get frequency, I'm going to try and rearrange it to get, wavelength on one side so I can substitute it in there. So I'm going to rearrange this. Frequency equals lambda equals C over the frequency. So now I can plug that in to this equation and I'm going to get a new equation. I'm going to get 1 over C over frequency equals RH times 1 over n squared minus 1 over n squared. So now let me fix this part because I got 1 over a fraction. I don't like that, so it's going to be like keep, change, flip. I'm going to get frequency over the speed of light equals the rest of that stuff. If I'm trying to get frequency by itself, let me get rid of this speed of light somehow. And the way I'm going to do that is I'm going to multiply each side by the speed of light. So I'm really going to get RH times the speed of light times 1 over n squared minus 1 over the other n squared. And my C drops out then. So I'm left with a new equation. Frequency equals the RH times C times 1 over n squared minus 1 over n squared. And now I can just plug and chug. So the RH, again, is at 1.097 times 10 to the 7 per meter times by 3.0 times 10 to the 8 meters per second times by, in parentheses, 1 over one of these n's. So I'm going to go, 4 squared minus 1 over 2 squared because the transition is from second to fourth. So those are my n's. And then I, beep pop, boop that and get an answer of 6.17 times 10 to the 14 per second. All right, if we take a look, per meter times meter cancels out. I'm left with just per second as my unit. Awesome. Final answer, Yahtzee. All right, last one. In this section, it says what wavelength of light in nanometers, so we're going to have to do some conversions here, right? So in nanometers, is emitted when an electron falls from the 6th energy level to the 1st in a Bohr hydrogen atom. Well, I know that I have this as my equation. Okay. So now, question is, I'm asked to get wavelength of light. So why don't I flip that so I get wavelength on top? So I'll just flip it. I get, wavelength over 1 equals 1 divided by that whole other side, RH times 1 over n squared minus 1 over n squared, right? And now I got to plug and chug, right? So now I just do, that's 1 over that RH number, which is, what did I write? 1.097 times 10 to the 7 per meter, times by the transition, which is going to be the 1 over 1 squared minus 1 over 6 squared. And then I'm going to get an answer of 9.38 times 10 to the minus 8 meters. So now if I'm trying to get nanometers, right, so I got my answer in meters, I got to think of a conversion factor. Well, I know nano means 10 to the minus 9. So if I have a nanometer, that's 10 to the minus 9 meters. That's my conversion factor. So I'm going to times that by, well, I want meters to cancel out, so I got to put meters on the bottom. 10 to the minus 9 meters is 1 nanometer. So now I keep doing my math. You go, all right, there's 9.38 times 10 to the minus 8 divided by 10 to the minus 9, and I end up with 93.8 nanometers. And that should be my final answer. All right, I hope you found that helpful. I'll see you in class. Okay, bye.